Now we're going to share our experience for the robot design and robot game. In this presentation, we'll cover the topics of robot design, attachment design, programming, navigation techniques, game strategy, and testing. Each season, FLL will publish a robot game, which includes 15 plus challenge missions for the teams to compete in a game field. Each team is required to design and build a Lego robot, and program it to complete as many missions as possible in 2.5 minutes. In the Cargo Connect season, there are 16 missions. Some missions are relatively easy. For example, the robot can simply push a cargo into a circle area, while some are very difficult. For example, one requires the robot to unload cargo from one target, then place it accurately onto an unstable ship deck. There are also shared missions for both teams to complete together. Next, we will share our experience on how to solve these challenges.
The first thing you should focus on in your season is to design and build a robot, which will compete in the robot game. This robot will navigate across the game field and use the attachments designed to finish the targeted missions. The robot will be made entirely of LEGO Grand Technic parts, like beams, axles, gears, and electrical components, such as bricks, hubs, motors, and sensors. The number of electrical components used need to meet the competition requirements. You can build a basic robot using either the LEGO EV3 kits or Spike Prime kits. In this talk, we'll focus on the EV3 robot. The EV3 brick serves as a brain for the robot and runs the programs for missions. It can connect up to 4 motors to the ABCD ports and 4 sensors to the numerical ports. The large motors are very powerful and are generally used for driving wheels. The medium motors are smaller and less powerful. They are mainly used to activate mission attachments such as lift-up arms. Sensors are widely used in the robot designs to measure and collect data from the game field for navigations. For example, the color sensor can measure the color and darkness of the map. You can use this to help follow a line or align robots vertically to a color line with 2 color sensors. These are popular navigation techniques to help the robot travel accurately to the mission model. The gyro sensor detects how much the robot rotates during its move and is used to help the robot perform different types of turns. PowerTrain designs and wheel dimensions have big impacts on the robot's size and overall stability. Generally, we prefer to design the PowerTrain module as compact as possible. In the top left example, 2 large motors, 2 medium motors, and 1 gyro sensor are tightly connected in a very compact design, which saves a lot of space for the robot. The choice of wheels are also important. The large motorcycle wheel can drive faster but less stable, while the wider automobile is smaller but more stable. You need to experiment with different types of wheels to find the best ones for your robot. To mount the wheels on the robot, have beams or panels supporting them on both sides, which will provide better stability for the wheel. The color sensors should be put in the front corners of the robot, facing downwards and close to the ground. This will allow the robot to detect the colors accurately and maximizes align accuracy. You should place the brick in a position where you can easily access it and efficiently during the runs to save time. Make sure it's well balanced at the center of gravity. For the gyro sensor, when it's placed between the 2 driving wheels, it's closer to the turning axis, and it can detect the robot turns more accurately. Having a compact and sturdy robot is essential. With a compact robot, the navigation will become easier and traveling across mission models will be more reliable. Creating extra support for the powertrain and chassis can make your robot strong and sturdy. It prevents the robot from breaking apart, which could be a disaster in competitions. Box robots is one of such designs with a rectangle shape and compact, strong build. It also makes the wall alignments much easier and allows faster and more reliable attachment switching. Thus, it's very popular in competitions. To make the robot more compact, you can design a compact powertrain module so motors and sensors are put closely together. Using LEGO tech pieces such as panels, rectangle frames, L-beams, or beams with perpendicular holes are very useful for creating a strong connection for chassis designs.
Attachment design is an integral part of the robot design, where we create efficient,
and created devices to help the robot solve the mission easily and reliably. You can use very simple attachments to complete a mission or design complex ones to finish few missions together so you can use your time efficiently. There are a few tips for a good attachment design. Try to find simple and efficient ways to build the attachment so it can be more reliable. Build strong attachments so they won't fall apart during missions. In case your attachment is contacting the mat or the wall, we suggest to add small guide wheels to reduce the friction. Use pinless installations so you can easily install and detach the device. There are many types of attachments you can create, such as plows, forks, hooks, one-way doors, claws, and forklifts. They can be used to do motions such as pushing, pulling, lifting, dropping, dumping, placing, delivering, releasing, capturing, collecting, shooting, and turning. And generally, these involve the following sources of energies: gravity, leverage, elastics, and motors. Attachments are awesome. There are two categories you can put attachments into: passive and active. Passive attachments are attachments that don't need a motor to operate. They're good for doing simple tasks like dropping things into a circle, pushing, and guides. When combined with a trigger release mechanism, it can be very efficient for missions. Active attachments are the exact opposite. They use motors to move and to do missions. These attachments are good at lifting and lowering slowly. It's desired to create a modular design for power transfers between motors and your attachments. In this way, you can have various types of rotations, powers, and distance transfers for more flexibility of your designs. There are universal installation interfaces, so you have to do less maintenance efforts. There is also faster attachment changes. To install attachments on the robot, it's preferred to create a pinless or a slide-on attachment so they can easily be switched during the robot game. You can create a multi-purpose attachment to solve multiple missions with just one attachment, or you can create a multi-mission attachment so you can solve multiple missions in parallel. Both types of attachments need extensive design iterations to arrive at a robust design. Digital design is very helpful to explore as many ideas as possible. It allows you to design attachments and robots quickly and easily without the need of expensive parts, and help you to always keep records of your old designs. We use Studio 2.0 as our CAD tool.
The robot needs to be programmed in order to navigate close to mission models and complete the missions. There are three commonly used programming languages for LEGO robots: Scratch, LabVIEW, and MicroPython. Both Scratch and LabVIEW are block-based programming languages, while MicroPython is a text-based one. Mindstorm LabVIEW was the most popular programming language for EV3 LEGO robots, and there's lots of free online tutorials available. However, the support from LEGO has been stopped, and most teams start to switch to Scratch or MicroPython. All the languages offer the basic functions to control the motors, such as drive the motor at a given power or speed, rotate the motor for a certain angle, rotations, or time, or stop the motor slowly or abruptly. You'll need to use motor controls to program the robot for driving straight or making turns, or control the mission motors to activate the attachment. For precise control of the motors and robots, you'll need to build complicated modules to make sure the robot can navigate as accurate as possible. Sensors are very important for robot navigations. The robot needs to be programmed so it can use various sensors to collect data from the game field to help navigation. With the color sensor, the robot can read the color or reflected light intensity of the mat so it can decide when to stop, how to align to a color line, or follow a line to navigate. With the gyro sensor, the robot can know how much angle it has changed during the movement, so the robot can adjust its position properly. It is highly recommended to create sensor calibration programs to help the robot sensors adapt to competition environments before the game, so the robot can reliably navigate. Generic flow controls are used in the programming for navigations as well as attachment activations. For example, An if-else statement can be used when the robot needs to follow a line based on the color sensor detects. While statement can be used when a robot needs to keep moving before stopping on a black line. And lastly, the for loop can be used if the robot needs to repeat a certain action. To program effectively and productively, you need a good platform to organize your coding. We have tried both Google Classroom and GitHub, and they both can be used to document ideas, report issues, and record fixes along with our code development. This allows our team to communicate progress with each other so everyone could continue the work. When making changes to your code, it's a good practice to add proper comments that document the time, the reason for the change, and how the changes are implemented. This will help your team to track the records and understand the changes better.
The robot needs to navigate closely to mission models to complete tasks. For missions that are easy to approach, the navigation could be simple and only need the robot's straightforward move. However, for missions that are further away and scattered around, the navigation could become very complex and might involve a lot of turns and alignments. Going straight, turns, aligning on the walls, and aligning on color lines are basic navigation techniques that help the robot move and position in the game field. It should be noted that for complex navigation routes, there are navigation errors, and these errors could easily add up so that the robot might fail to solve the targeted missions. Accurate navigation is one of the toughest tasks for FLL challenges. In order to go straight forward, you need to first find out what the wheel diameter is. Then, multiply the wheel diameter by pi to get the circumference. Now, program the robot to divide the travel distance by the circumference, so it can find out how many rotations it should rotate the wheel to get to the desired distance. There are two types of basic turns generally used during navigation: spin turns and pivot turns. The robot can turn either left or right. Spin turns are usually faster since both wheels rotate. The rotation of one wheel is negative, while the other is positive. In pivot turns, only one wheel moves. Pivot turns are usually used near walls. The robot turns are generally not very accurate, so you'll need to correct the errors. You can also use alignment techniques to help the robot correct its position on the game field. There are three kinds of alignments: wall alignment, mission model alignment, and line squaring. In wall alignment, the robot aligns on the wall by moving back for a certain amount of time. For mission model alignment, the robot aligns itself on the model so it's facing the right direction. This alignment is not always accurate. For line squaring, the robot aligns on black and white lines with the help of two color sensors. You can do multiple alignments to make it more accurate. For this alignment, always use low power so you don't skip over the lines. To improve the accuracy of navigation, the robot needs to be able to detect error and correct it. For example, when turning, the robot makes a quick turn and then uses the gyro sensor to find out how much more or less it went over the target angle. Then, it makes another slow turn to fix the error. Finding the errors and correcting them can also be used for go straight movement.
The robot game is very exciting, but can be very challenging. There are more than 15 missions to solve with tasks of various difficulties, and it could involve a lot of mechanisms and algorithms. It also takes time to switch attachments to the robot, and the robot needs to navigate across the table. It's extremely difficult to finish everything within the 2-minute 30-second time frame. Plus, there are a lot of uncertainties. Your robot or attachments may not be built strong enough so that they could break during the game, or your program might have some bugs so that a robot does not do as you expected. Competition environments are always different from where you've been practicing, and there could be human errors, and sometimes a lot. To prepare for these, you'll need to be well planned. It's very important to study the robot game rulebook carefully so that you can clearly understand the detailed mission requirements and build the models correctly. Also, with a deep understanding of the game rules on the equipment setup and operation guidelines, you can avoid penalties during the game and maximize your team's score. The FLL Challenge updates will be published online every couple weeks to clarify potential ambiguities, so keep an eye on it. Mission analysis is the process of brainstorming possible solutions for individual missions. To get a good idea of how you should go on solving the robot game, you can sort out the missions based on their difficulty level, navigation distance, attachment and mechanism type, etc. We recommend creating a spreadsheet to document all your thoughts and discuss them with your teammates. And then focus on a simple and easy way to score missions first and prototype your solutions, such as you could create a lever to push down a button or design a cart to move containers. There are many possible solutions, and you could always work out a simple one that is very reliable and compact. Since the game time is limited, you may want to group many missions together in one launch so that the robot can complete them in just a few trips. Keep in mind that both reducing the attachment setup time at launch area and minimizing navigation trips will help, since then the robot can spend more time completing missions. Here are a few tips on planning the group missions. So you can group missions together when they can be solved using similar attachments so that you can save time from switching them. Also, you can group missions too when they're very close by. In the robot game, you actually have an advantage in the fact that you have extra time to install your first attachment before the run. You can use this to install your most complicated attachment so that you won't have to waste time setting it up later. Putting high-scoring missions first is a good idea since you can always rerun them if they fail. You'll need to practice a lot to find problems to keep improving your solutions. Here are a few tips based on our experiences. First of all, you may want to prepare a game checklist, which includes make sure you charge your battery, calibrate sensor, check on motor conditions, check on cable connections, and formulate a rescue plan. Also, you can practice reducing the setup time in launch area. You may also want to try leaving attachments on the field to save time switching. However, just make sure that you don't leave them in a place where they would block the navigation. You can also try rearranging the launch order to find the best combination for your time. Also, make sure to be ready for any failure or surprises.
When you have multiple designs for your robots, you can perform systematic tests to figure out the best one. Durability and mechanical tests evaluate robots' shape, size, sensor placement, wheel configurations, and powertrain design to decide which best fits for competition. Navigation performance tests check how fast and accurate your robot performs basic movements, such as turns, move straight, and alignments. Then you can design simple and complex navigation routes to check whether the robot can consistently and accurately perform the task. Attachment testing starts from individual mission devices, where you find out the better candidate solutions. When combining multiple devices for grouped missions, you'll need to test on different configurations to find the most efficient and robust ones, how they can be integrated with power sources to perform tasks, and whether there's a need to redesign both the attachment and navigation route when everything is integrated. You should improve your designs for the problems found during these tests. To ensure consistent runs, test your design and game strategy with multiple runs to see if it can repeat the same results. To improve on this, try different attachment and navigation solutions to find the most reliable and efficient one. You can make improvements in the code and attachments to ensure the greatest consistency in both navigation and attachment operations. Also, make sure your attachments are strong and robust enough so they don't break during the game. To have good efficiency, you can adjust the driving speed for motors, design better navigation routes, or perform multiple missions in parallel, and test to find the best combinations. To finalize the overall solution for the full run and ensure it's efficient and robust, there are a few measures you need to take. We suggest finding the part that's most prone to failure and keep testing and adjusting it until it's robust. Also, you need to finish the game in 2.5 minutes, so create a launch order. The missions that easily and consistently score, earn a lot of points, or require a longer setup time should go first. Split the setup tasks between launches with your partner so you can finish them efficiently. Create a plan in case there's a problem with the robot and you need to rescue or fix it. Finally, always document your testing, results, and the problems found to share with your teammates for further improvement. Thank you.